Okay, so we're looking at a closed adiabatic reactive process. I've made a beautiful drawing here of that, and we want to write an energy balance so that we can keep track of the temperature inside the tank here. So let's do that. And we'll start out with the most general balance that we have. We could think of work being added to the system, and thus changing the energy of the system. The same thing goes for heat. And there might be some energy exchange due to flow and due to reaction. And all of these contributions have the effect that they change the internal energy of the system per time unit. Now, the fact that the system is closed means that there's no flow in and out. That means that this term here is 0. And the fact that it's an adiabatic process means that there's no heat exchange with the surroundings. So this term disappears as well. And we will choose to neglect the work done to the system, or the work that the system does to its surroundings, because it's not a considerable amount. There is an agitator here, but the energy that it puts into the system is negligible compared to the reaction energy. So that simplifies our energy balance quite a lot, and let's see if we can expand on it. So the energy of reaction here we can write as L times R times V, and the right hand side we can write as M times C times the time derivative of the temperature. So here we have the specific heat capacity, here we have the mass of the contents of the tank, here we have the volume of the tank contents, and L here is the heat of reaction, and we measure it in joules per mole. So it gives us the amount of joules that is created for each mole that reacts. And R is, we know that one, that's the reaction rate, and it's measured in moles per liter times minute, for example. That could be 1 unit. And this is the volume of the system. Let's look at the reaction rate here. If it's a first order reaction, then the reaction rate is given by a reaction rate constant times the concentration of the reactant. And I should say that when I say C here, the concentration, I mean the concentration of the reactant. And maybe we should put an A over here as well, like that. So that means our energy balance looks like this. And note that this A here is not an exponent. This is not a power of C. This is just an index, indicating that we're looking at the component A here. Now, this is kind of bad news because we're now introducing a new unknown function, because this is actually a function of time. We know that there's a reaction going on in here, so the concentration of A is bound to change. We know it's going to drop as the reaction proceeds. So now we have two unknown functions, the temperature and the concentration. So what to do about that? Well, we need another equation. And we'll use the fact that the change in concentration of the reactant per time unit is equal to minus the reaction rate, and that in turn is equal to K times the concentration. So this gives us another differential equation, and that enables us to solve this problem. Now we can make it more refined, keeping in mind that this reaction rate constant is actually a function of temperature. And we can use the Arrhenius equation to specify what kind of function this is. Namely, K naught times e to the power some parameter minus a over the temperature. This parameter is an empirical constant from experience. So this gives us an energy balance which becomes quite involved. Like this, equals mc d capital T dt. And of course we should incorporate that into our concentration differential equation over here. Like that, oops. So here we have one differential equation, and here we have another one. And look how they are coupled together. So this derivative of the concentration depends both on the concentration and the temperature, and the derivative of the temperature depends both on the concentration and the temperature. So they're coupled together and they are nonlinear. I'll just rewrite this. So that I isolate the derivative L times K naught e to the power minus a over T times Ca times V divided by M times C. And if you remember that M is actually equal to the density times V, then you can see that V over M must be 1 over the density. So I'm able to replace these two by 1 over the density. So I'll simplify the equation slightly. Like this. So here we have the second differential equation. Now if you plug these two into, say, SymPy, you won't get an answer because these equations are too complicated. They're nonlinear and coupled. SymPy simply can't solve them. So we have to resort to different means. We have to do a numerical solution of these equations, and I'll show you how to do that in the next video.